Hello, everyone, and welcome to all. My name is Saad bin Saeed Ahmed. Am I audible? Uh, I'm audible now?
Yes, you are
Thank you very
audible.
much. Thank you. So, thank you very much for the opportunity. I would like to thank MPTF for giving this platform. My name is Saad bin Saeed Ahmed. I am a medical physicist at Afan University Hospital, Radiation Oncology. Today, I'm going to present some fundamentals about radiomics and its application in radiotherapy. So my outline would be about some basic definition of radiomics, some history of radiomics, how we can extract radiomic features, some what recent trends in radiomics are, how the application of radiomics in radiotherapy is, what is the basic radiomics workflow in radiation oncology AKU, how we are doing and applying radiomics for predicting outcomes, and some highlights on the ongoing projects. So just for a glimpse of the history after the discovery of X-rays, there was a gradual increase in medical diagnosis with the utilization of X-rays and technology, and with the introduction of new modalities with time to time, like PET scan in 1961, then CT scan, then MRI and PET CT. There are on continuous intervals, we saw some computer aided diagnosis being done on different by different individuals. So the term computer aided diagnosis was termed in 1963. It's basically using computational features to diagnose some disease from by with the help of imaging. And the first texture analysis was done in 1973, and some texture features were proposed in 1973. And the first patient which was filed with the help of texture analysis is 1987. And the term radiomics is being coined in 2012, quite recently. So by definition, radiomics is a technique or a set of tools by which we extract clinically relevant, or you can say quantitative information from medical imaging. And what's the application of this? It can be beneficial in early detection of the cancer or any suspicious lesions in radiological images with the help of its density and its pattern. And also it can be helpful in characterization of a sample or you can say tumor or any other metastases. To categorize them, radiomics can help you to categorize these different type of malignancies on the basis of correlation with clinical information. Also, it can help to determine or predict treatment response. So radiomics has a role in detection, characterization, and also treatment response evaluation. So radiomics has application in almost all of the medical imaging, either it's functional, anatomical, molecular. Recently, all of these type of images have radiomics applications, and there are a lot of publications coming out recently on all of them. So to determine basic, or you can say the classical radiomic workflow would be, in first step, you need to acquire images. Either you are doing it prospectively or you already have a set imaging data set. You just need a imaging data set. And that data set should be of similar nature, because the radiomic feature which you are going to extract from these images, they are very sensitive to the quality and specification of the images. So the first step is image acquisition. And next step is image pre-processing. Basically, pre-processing is like you need to filter out images on the on a different level of specifications. For example, if their acquisition parameters are different or their scanners are different. So you need to resample, filter, and normalize the data set, what you have for radiomics before going for feature extraction. In next step is ROI segmentation. ROI segmentation is basically you are specifying the area for, or either it could be a target volume, GTV, OAR, for which you are going to extract the radiomic features. So in case of oncology, it could be a GTV lesion or any OAR for which you are going to extract the radiomic features. The next step is feature extraction. For feature extraction, there are different open softwares are also available, or there are language-based programs for which we can use we can use them to extract radiomic features. And the next step is the correlation of the extracted radiomic features with the clinical information we have. And once we correlate all the radiomic features we have with the clinical information, then the statistical analysis help us to separate the specific or significant radiomic features from the rest of the others. So those features would be helpful in the detection, characterization, or any clinical application. So this is basically the workflow of radiomics. So let's have an example. For example, this is a lung. We have a CT scan from lung, and we segmented a portion of or volume from that patient scan. And if you translate on the basis of pixel and its and its intensity values, so it on the right side is the histogram of this one. So if there is a good segmentation, the data set have low noise, and if the segmentation is not good, if we just took a square box, then there would be more noise. So segmentation is the key. If there is a good segmentation, is bring more significant or better radiomic features. So this is how we do segment the section which we are going to take for the radiomics analysis. Okay, so radiomic features, if you we can divide them into categories. One is semantic and other is agnostic features. So the semantic features were usually being used by radiologists to describe the shape, lesion, or localization, either vascularity. Mostly the clinical terms being associated with these features, and they are usually being specifying the type, shape, and the volume of the lesion, and they are mostly related to the volume or shape of the lesion. The agnostic features, they are basically the one which are being mostly used in radiomics. So radiomics agnostic features, there are several orders of the agnostic features. The first order or the simplest one are like, you can say mean, mod, median, being taken out from a specific voxel or a piece of image from which you took the, for which we do the segmentation and apply the radiomics analysis. So the first order radiomic features would be very simple one, like mean, max, mod, median. But these features are not enough to specify because there, for example, you can see here, these two pictures have, or these two segments have same values for mean, mod, median. So the first order radiomic features are not just significant to process radiomics analysis. You need more high order features which have some textual information and advanced information to be correlated with clinical information. So that's why we have more higher orders of radiomic features. So let's go for the higher one. So second order radiomic features, basically they are being statistically deduced, or they are statistical descriptors. And we can also call them that they have the ability to identify the textures, because they have both informations of intensity as well as spatial information of the pixels. So they are incorporating both things. That's why we call them texture features. And for example of these second order features are gray level coherence matrix and gray level run length matrix. I am just going to give some example of these two, how we are going to calculate. For example, we have a segmented section of a picture and it has values. For example, these are gray level values from 0 to 3. And if you want to calculate the gray level coherence matrix for the left hand part, what we have to do is just define a matrix, and we check how many times similar values are being occurring in this left hand side. For example, the 0 and 0, the pair of these zeros are appearing twice here, so we just write 2 here. So that's how we are putting the information from the picture element into the matrix. And one more example is like how many times 2, the gray level of 2 or a pixel value of 2 is appearing together. So here you can write it's 3 times 2 and 2 are appearing. So that's how we are translating the co-occurrence of similar pixel values from the picture element to the text. And once this matrix is generated, we can apply many different mathematical operators on this one and get a single value. That single value would be a radiomic feature. Similarly, we can calculate if we have the gray level co-occurrence matrix once, we can have all these values. For example, we can have a contrast. We can measure contrast with this one. We can measure the correlation like a measure of gray level independencies in this section of the picture. It's an entropy, how there is a randomness of gray levels with respect to the spatial information there in this element. Or we can also calculate the angular segment moment for this, which is describing basically the homogeneity or non-homogeneity in the specific element of the picture. Another classical radiomic feature is run length matrix. Run length matrix is basically we are calculating that in the picture element which we selected or segmented, we have 4 gray levels like 1, 0, 1, 2, and 3. So how many times if we run length from left to right, how many times a specific gray level is being appearing. So we just start putting the values in the right one. And once we have this matrix set up, we can calculate further like gray level non-uniformity, gray level uniformity. And these are basically once you have the values for these one, you have the radiomic values of these features against these features. And these classical radiomic features were first calculated in 1975 by Galloway. So these are basic classic radiomic features. And now if we have a lot of derived radiomic features from these basic ones. So to summarize, that high order radiomic features like GLCM, GLRLM, and GTDM, they are basically what they are measuring is they are measuring the co-occurrence, how similar voxels are co-occurrence in neighboring, and how basically the homogeneity is, or there is a non-homogeneity, how is there any entropy in the controlled or segmented section. So these radiomic features are basically calculating the randomness or homogeneity, non-homogeneity, or any sort of texture correlation between pixels occurring in the selected feature. So that's how this is the quantities which are radiomic features being measuring. And once you have these one, you can translate them into shape-based parameters, or if we have a lot of image data sets and a lot of radiomic features, we can translate them into also signals. So let's have a larger picture now that radiomics is like on the cross section of medicine as well as computer science and also statistics. This is been converging as a all of this is a converging field of all these medicine or advanced computational techniques. So, but all of them have a unique goal, or you can say one goal is to make patient care better. Just to have the idea that how radiomics is being the radiomics emerging as a field of study. So this review article was published exactly like last year, and you can see it is showing that the number of publications in radiomics, and you can see here that in 2020 it's around 3,249 papers. And I'm sure if there is a new review paper on the literature of the radiomics, it would of this year, it would be more around 8,000 or 7,000 papers per year. Okay, so how radiomics is basically giving edge in radiation oncology. So in most I here are mentioned few stages, like in stage of diagnosis, radiomics is being performing very well. They are giving there are many models which are available to on the basis of radiomic features. They are giving early diagnosis, and some of have very good accuracy. Also in planning, for example, in treatment plans specific to the brain or in lung, where the margins are quite tight. So radiomics is very helpful in contouring and segmentation of these high dose plans. Early adoption is quite possible with radiomic studies, and there are many radiomic studies in brain which help to which help a type of which can predict the adoption on the basis of significant radiomic features, so that their multiple plans can be planned early to save the time. Predictive models, there are available predictive models for different type of radiation for the tumors which are being going through the radiation therapy. So they can predict the outcome or even type of if there is any associated risk of the treatment or the type of outcome it would be. The radiomics features are available for this purpose. Also, its radiomic features are helpful in applying and giving idea of follow-ups. And also with the follow-up scans, there is a potential to compare the radiomic features, and it can help to predict the type of or differentiate which treatment is good or better. So all of these stages have application for radiomics, and there are various studies being published in this paper which are associated to these different stages, giving an edge on radiomics. So earlier we talked about the classical radiomic workflow, and because with the emergence of AI and machine learning, the application of radiomics along with AI and machine learning enhance the output, and they are available. Radiomic features are available to make the models more effective. So if you are going and using an artificial neural network, so you can also add radiomics feature with this, and it would enhance the accuracy of the model. These are like two types, different types of workflows. One is for artificial neural network, the top one. And if you are using the AI and machine learning, even for the segmentation, which is one of these steps for the for radiomics analysis, it's also helpful to do the segmentation in earlier stages, which really help the radiomic features has application in segmentation as well as in correlation with the clinical information. So this one, the bottom one, the machine learning model has like you can say two degree of two stages of application radiomic features. So okay, so what we were doing in AKU as a radiomics project, we have patients for cervical cancer, and around there are 230 patients. We separate patients from on the basis of the CT, pre-CT and post-treatment CT scans, and we contoured the GTVs for uh, pre and post-treatment scans, and on the GTVs we have performed radiomics analysis, and with the extraction of radiomic features, we quantified the radiomic features on the basis of complete response and partial response. And we found like three to four radiomic features to be significant in this study. And these features have like potential to predict the response of the treatment in cervical cancer. So this is the project which is currently being going on, and the radiomics part of this project is completed, and now we are moving towards the incorporation of artificial neural network for the same in the same study. And another project which is also in progress with the Florida Atlantic University, the Mohammad's Lab. It's on head and neck. What we took is two publicly available data sets from the Cancer Imaging Archive. The set one has 31 patients, and the good thing about this set is we have 3 scans of each patient, which is pre, mid, and post-treatment scans. And for all of in this, the information of xerostomia about these patients also is noted. And what we did is we extracted radiomic features from the parotids of these patients and correlate with the clinical information of xerostomia. And we found few radiomic features which are basically corresponding to the level of xerostomia. This is a basic workflow. First, we already downloaded the image data sets, and then we segregate them. After segregation, we do image segmentation of OARs. Then we apply feature extraction with these radiomic feature extraction, and then we correlate the clinical information of xerostomia to the parotids with the of these images. Another study is about the normal tissue complication probability, and with the same data sets, we extracted the DVHs from these from the treatment plans of these patients, and we calculated the TCP and NTCP values with Redmode Bio and freeware software, and we use the radiomic features, the clinical information of these patients, and put them as a input for artificial neural network, and we try to break the NTCP values with this one. Another study is about the lung. The data set is also being downloaded from the Cancer Imaging Archive, and it's open source. And the information of these the data set was of different stages. First, we segregate them, and we also have the clinical information of these patients about the overall survival. So we extracted the radiomic features of the GTVs, and then we correlate the radiomic feature extracted from the GTVs with the information of overall survival, and we found some radiomic features which have the potential to predict the overall survival. all these works were presented in different papers and on conferences, and still some are in process, and we are try to finish these works in this coming year. So I would like to acknowledge Dr. Muhammad's lab and Dr. Muhammad Wazir for his guidance and mentorship, and also Radiation Oncology team AKUH for all this data sets and the clinical information and the support they provided along all these projects. Thank you very much. If you have any questions, you can ask.
I would like to ask you one question. How does it help to, I don't understand much. It is, yeah, we do CT scan, we do MRI for this, and we use this CT MRI for planning and radiotherapy. How does it help there, this system? Can you explain, please?
So your question is doing CT and MRI for the purpose of radiomic extraction?
Yeah, purpose of planning, radiotherapy planning. How
Yes.
does it help in radiotherapy treatment, actually? I just want to know.
Okay, so the project we did for like xerostomia, for example, the previous, let me go for the slides. So what we did, we have patient data sets which were already treated patients, and these patients, for these patients, we have CT scans. And once we extracted radiomic features from the information of CT scans, which were already taken for planning and follow-up purposes, we found some radiomic features which are corresponding to xerostomia. So once we know that this type of features are like more prone to be of xerostomia, so once we have a new patient and we have a CT scan, we just took the CT scan and we extracted the value of xerostomia. We extract the radiomic feature and try to correlate if this is the same radiomic feature or no. If we like this patient have the radiomic feature similar to one of those which were already treated, so we can like modify or alter our treatment plans on the basis of that information, and we can like spare his parotids, or we can add, or we can like minimize some sort of we can alter our plans, and we can save it to go from the level of xerostomia from high to low. It may be helping this one.
Okay, thank you. So is it a software?
Yeah, I can share. So for there are open softwares. I was using LifeX for the purpose of feature extraction, and for the developing of neural network, I'm using MATLAB. But there are Python-based codes, which also open source. You can use them to extract radiomic features.
Okay, thank you, sir.
Okay, so for the extraction of radiomic features, I'm using LifeX. I'm just writing the name of the software. This is the freeware. And for you can use MATLAB or Python for this purpose also. They have already built-in packages for feature extraction. And there are also free softwares like LifeX, Slicer 3D. You can use them for this purpose.